Hello, and welcome to this session on satellite monitoring for forest management, or SMFM for short. This session is organized by the World Bank and the Program Partnership for Sustainable and Resilient Landscapes. I'm Laura Ivers, Senior External Affairs Officer with the World Bank, and I will be moderating this session. Today, we'll be hearing about how satellite monitoring tools can contribute to improved management of dryland forests. To get started, I'd like to invite you to participate in a few polls to help us get to know one another. To join the polls, please scan the QR code on the screen with your phone or follow the link on the slide and also in the chat that will take you to Slido. If using the link, once you open the page, please add the code #GLFAfrica. Once in Slido, you'll see a drop-down menu to select our session. Scroll down to Satellite Monitoring for Forest Management and select it. You'll then see tabs for Q&A and polls. Click on the poll tab on the right, and then please go ahead and complete the first poll about what sector you work in. We'll have the poll open for about 30 seconds, so please go ahead as soon as you're in and go ahead and vote. We'll maybe leave it open a little longer just to give people time to log into Slido. So if you're still logging in, please continue to do so. Okay, well, we're seeing quite a nice distribution across sectors. So although I'd like to see more people completing the poll, I think in the spirit of making sure we have time to hear from the speakers, let's go ahead and move to the next poll. So the second poll, we're looking to understand a bit about how much you know about remote sensing, satellite data, and forestry. So please go ahead, take a moment to read the options for the answer, and then choose what best describes your understanding. Okay, so we'll leave this open for just a few more seconds. Well, this is great that as a baseline, we know that we at least have some knowledge of this topic going into this session. And I think you'll find that you learn a lot during this session, and we'll have another poll later on to check in on what you have learned. I also want to note that throughout the session, you're welcome to use the Q&A feature in Slido to ask any questions that you might have, and we'll do our best to answer those questions later in the session. Now, to give a preview of what you'll be hearing about, here's a video about the SMFM project.
Tropical dry forest ecosystems are estimated to cover 1.1 billion hectares, about 27% of the global forest cover, and represent a globally important carbon store. Some estimates situate the carbon sequestration potential of dry land ecosystems in Africa alone at around 0.5 billion tons of carbon per year. They are subject to some of the highest rates of deforestation and degradation around the world and support the livelihoods of large numbers of the world's poorest people. It is estimated that in sub-Saharan Africa alone, some 60% of the population depend on dry forests for their livelihoods. To properly conserve and manage tropical dry forests, countries need reliable information on its extent and condition and understand what drivers are causing change. Modern satellite Earth observation technologies combined with free and open access data provide opportunities to address existing limitations in forest monitoring capabilities. Emerging cloud processing services for EO data such as FAO's CPAL or ESA's FTEP platforms combine advanced processing algorithms with access to satellite data and significant processing power and storage capacity. To develop satellite EO methods and global knowledge for monitoring of dry tropical forest ecosystems and assessing forest degradation, the World Bank, with technical support from the European Space Agency, implementing the Satellite Monitoring for Forest Management Project. The SMFM project developed 4 tools specifically tailored to the need of forest managers that make use of free satellite, open source software, and EO cloud platform capabilities. The SMFM project has worked closely with the government agencies of partner country to assist in developing their technical knowledge and capacity for sustainable forest management and reporting needs, including RED+.
My name is Martin Schweter from Germany. My role in the SMFM project was team leader for the consulting consortium, which was composed of LTS International, a Scotland-based consulting firm, and the University of Edinburgh, equally from Scotland. Our team led the co-development of the SMFM tools, which is a set of lightweight remote sensing tools, particularly built for tropical dry forests. And we provided the capacity building and training to the counterpart personnel in our project partner countries. The SMFM tools really added a new perspective. What was interesting to see was how the initial skepticism on the part of the forestry departments we worked with gradually vanished and changed in the course of the project. At the end, it was fully acknowledged by all our partners that this is the way to go in the future.
Hi, my name's Sam Bowers. I work as a postdoc at the University of Edinburgh. In producing the SMFM tools, we had a close collaboration with the teams in Mozambique, Namibia and Zambia. We found these teams to be committed and knowledgeable and willing to tell us exactly what they needed in order to get their work done. Working in science can often feel very abstract. The objective was to ensure that the SMFM tools were practical and useful.
One of the things that these countries do is they produce land cover maps to monitor the state of land cover and how it's changing over time. However, accessing cloud-free images can be very, very difficult. What we have provided here is a pre-processing chain to take in data from Sentinel-1 and Sentinel-2 and produce wall-to-wall maps that can be used for land cover mapping. These routines take freely available data as input, which will be available into the future, having been pre-processed to the point where they're ready to use. One opportunity that we have when working in dry forests is that these forests don't have the same density or the same biomass as tropical rainforests. SMFM Biota is calibrated to produce maps of biomass and biomass change. Biomass is a useful parameter for measuring the state and condition of your forests, and biomass change can be indicative of deforestation or forest degradation. Forest monitoring agencies want to produce statistics for the rates of their forest change, but often these statistics are backward looking. What many active managers would like is to know where things are changing now. SMFM Deforest is a dense time series tool. It takes in all of this information to produce maps of deforestation that are up to date and also provide early warnings of locations of possible change. The final SMFM tool takes cues from the shape and the location of change events to try and predict what the causes were. For example, we might find that commercial agriculture changes have a large area, and we might find that the texture of changes from, say, charcoal production or wood fuel harvesting might be quite distinct. In using these clues, the tool aims to identify the locations of changes that are occurring and what their causes were.
I'm really pleased and really satisfied to see that ultimately forest management and forest monitoring in tropical countries is going digital. We had the pleasure of working with young, smart forestry officers that fully grasped the opportunities offered by the SMFM tools. And they used whatever they had, sometimes just a laptop, to tap into the online satellite data resources and leverage on cloud processing performance to produce really, really encouraging results. I therefore truly believe the SMFM project will leave its mark on monitoring of tropical dry forests.
Making efficient and effective use of modern EO technology can lead to improved and more reliable reporting on tropical dry forests, allow for reactive action against early signs of deforestation, and contributing to a better understanding of degradation in dry forests and what drivers are behind change in this ecosystem. For more information, visit www.smfn-project.com.
Next, we'll hear welcoming remarks from Ida Paswari-Radehu, World Bank Country Director for Mozambique, Madagascar, Mauritius, Comoros, and Seychelles in the Eastern and Southern Africa region.
Welcome to this session on the satellite monitoring for forest management projects. This is the kind of forum and discussion that would have been great to have in person. Unfortunately, the times have changed, and so we adapt. And despite the challenges of today, forest management and good use of these resources is a must, and must remain at the center of how we interact with the environment. Furthermore, had it not been for prior engagements, I would have been honored and very happy to join you virtually. Having studied forestry myself, focusing on how its management can enhance its productivity and environmental services, I could not resist joining you, even if it were only by video. Today's topic is fascinating, and I will make time later to watch the video from today's presentations and discussions. Bringing all of you together, government colleagues, practitioners, and researchers from all around the world, and especially from dry forest countries in Africa, creates a powerful platform to share and to learn from. Climate change and COVID have demonstrated just how impactful these events can be on people and the environment. I remember watching an incredible video a few months ago after COVID became quite serious. And most notable in the scene was how nature was reclaiming the space back that we had a much lower impact. What this tells us is that we need to support growth post-COVID, but from perspectives of policy and investments that are greener and more resilient, and that have a much lighter touch on the environment itself. What's clear is that it will not be an either-or situation, but one of balance after identifying the challenges and the opportunities. For that, we need reliable information on natural resources, their condition, and the human impact on these resources. Without adequate data, our policies and actions are likely to not achieve the impact that we desire. There is ample evidence that remote sensing and satellite monitoring are powerful tools in obtaining the information we need. When combined with robust field observations and scientific data, we can obtain information and knowledge on large areas in a very cost-effective way. Sustainable landscape management is central for our work in the bank. The satellite monitoring for the Forest Management Project focused on dry forest landscapes. In sub-Saharan Africa alone, approximately 320 million people rely on these dry forests for their livelihoods. If resource access and use are not well managed, ever-increasing pressure on these resources at the local levels can have ripple effects that are felt at national, regional, and even at global level. Being the current World Bank Country Director for Mozambique, one of the countries where the project developed many different tools, I'm particularly happy to see Mr. Aristides Muhate from the Fundo Nacional de Desenvolvimento Sustentável among today's speakers. In Mozambique, sustainable forest land and landscape management have been essential elements for the bank's engagement for many years, and currently we are deepening this engagement in landscape management. For example, through a rural resilience program in the northern part of the country. Data and improved knowledge have always been a central part of our engagement, evidenced by our support to the recent National Forestry Inventory. The inventory has allowed Mozambique for the first time to submit its forest reference emissions level to the UNFCCC. Congratulations, Mozambique. Further, it is worth mentioning that Mozambique recently became the first country to receive the REDD+ emission reduction payments under the bank's Forest Carbon Partnership Facility. The tools developed by the SMFM project played an important role in this achievement. Still more needs to be done to mainstream the many tools developed in many more countries in Africa. Where the bank is engaged, we stand ready to support these efforts. I would like to wish you an excellent session, excellent learning, and excellent contribution, and I look forward to watching the video. Thank you very much for your attention.
Now, I'm pleased to introduce our first presenter today, Tuka Kasprin, the task team leader for the SMFM project. Tuka is a senior forestry specialist with extensive experience related to forest governance, forest finance, and the use of ICT and other technology for sustainable forest management. Tuka currently works in the World Bank's East Africa unit. Without further ado, over to you, Tuka.
Thank you, Laura, and good morning, good afternoon, good evening, whichever time zone you are in. Let me share my screen. Like mentioned, the satellite monitoring for forest management project was a knowledge development project that the bank implemented with a large group of partners from 2017 to 2020. It was financed by the Global Environment Facility, GEF, and its objective was to, like we've heard, improve methods for satellite monitoring of tropical dry forest landscapes and forest degradation, and making these tools available to countries. So why did we do this? For two reasons, for two simple reasons. First, it's important. Dry forests have huge local importance for food security, and they are also an important source of medicinal plants. They contribute to local rural livelihoods through non-timber forest products, pastures, agroforestry systems, and often they are the only source of fuel or construction wood for people living in these landscapes. And they also have huge global importance. They are a carbon stock. We don't exactly know how big a carbon stock, but still a very important carbon stock. And they obviously are also very valuable for their biodiversity. But at the same time, these landscapes are under increasing threat from agricultural expansion, from degradation, from overgrazing and overharvesting. There's an increase in human-induced fires, and we also know that climate change will impact these landscapes. And the second reason behind the project was that it's possible that we can, if we develop the right tools, monitor forests much better and efficiently than we've done before. New satellite missions like Sentinel satellites by the European Space Agency, Landsat by the Americans, ALOS by Japan, and many, many others have brought us unprecedented access to satellite data. Various RED programs have developed good monitoring methods and tools for tropical moist forests and land and rainforests, but much less attention has been paid to dry forests despite their importance. Therefore, in the project team, we made a decision to focus on this largely underappreciated forest type. At the same time, with improved access to satellite data, there has also been an improvement in the way we process the data. Cloud computing tools and various processing platforms have made it easier to process the data. It's no longer necessary to download huge volumes of data, and this has been a major constraint, for example, in many African countries, where bandwidth has been a concern. With cloud computing, you only need to upload the script and queries and download the results. Obviously, it's a simplification, but that's the general idea, and that's the way we are heading. With the SMFM project, we aim at developing operational tools that would give forest managers useful tools in their work. The tools were aimed at providing reliable information about location and extent of dry forests, information about the condition of dry forests, information on ongoing change, and data to evaluate historic change and patterns of change. And also, we aim to produce tools to assess the data on drivers behind change in dry forest cover. I want to emphasize 2 points here. First, the aim was to develop operational tools, not just something for researchers, but also practical tools for forest managers. And second, while we hope that these tools are useful for REDD monitoring and climate change monitoring, at the same time, we recognize that satellite data can help other aspects of forest management, governance, production planning, the public engagement, transparency, etc. Generally, or overall, the project consisted of 3 generic phases. However, the way the project was implemented, 3 different stages, these 3 different stages were very closely interlinked, and in practice, there was no clear distinction. The first phase was the actual development of the tools. The first versions were developed at desk work. This work involved the actual coding and running test versions of the tools. But the main aspect and main approach, like we heard in the video, was co-development with practitioners. This meant that end users and researchers worked together in creating and developing and testing these tools. Sam Bowers will later tell us more about the tools themselves and their development process. But the main idea was that the tools were developed through several iterations where user feedback helped us to develop them. The second equally important part was capacity building in various aspects of the project. This included both activities in practical forest operations like planning field campaigns and measurements, and also more technology and data processing related issues like Linux and Python, as well as radar remote sensing technologies. The third important part of the project was doing field work. This was most visible in Mozambique and Zambia, where we had extensive field campaigns, field missions to collect data in situ. In Namibia, we had slightly different approach. Here, the available data sets allowed us using existing data as training data for the tools. And this was an interesting case study since the SMFM tools are meant to be used globally, and it was valuable to see how, quote unquote, a new country can start using these tools without extensive data collection before using them. We aim to have the 4 tools developed, used as widely as possible, with or without projects supported by development partners. The project was based on the assumption that we are gradually moving towards a situation where even relatively advanced remote sensing tools are available to forest agencies widely rather than only to research organizations. We are not yet there, but I believe that we are moving towards that direction, and therefore it was essential to test these tools, how operational they are in practical conditions, and work with forest agencies in using them. But we obviously were not able to do this alone in the bank. The 4 remote sensing tools that we developed were a result of a wonderful partnership. It took 4 international organizations. The Global Environment Facility, GEF, provided finance. The Regional Center for Mapping of Resources for Development, RCMDR, provided training and regional networks. And the European Space Agency, ESA, was our scientific partner, and it provided access to data. A team from the University of Edinburgh and consulting firm LTS International led the practical work and provided also scientific knowledge. And the governments and forest authorities in the 3 fieldwork countries, Mozambique, Zambia, and Namibia, were essential partners in making all this happen. I think this shows that the complex challenges of landscape management, when we try to solve them, we simply don't have any substitutes for partnerships and working together. So this was very, very brief summary of the satellite monitoring for forest management project. The tools that were developed help us to create mosaic images from Sentinel data, measure biomass change, develop dense time series of forest change, and assess the types and drivers of forest change. Like I said, we will hear more about the tools themselves shortly, but I sincerely hope that this session triggers your interest in using these new and innovative tools. So thank you very much. And again, welcome to our session. Laura, over to you.
Thank you, Tuka, for that overview and background on the project and tool development process. Our next speaker, Phoebe Odur, a remote sensing specialist from the Regional Center for Mapping of Resources for Development, RCMRD by its acronym, based in Nairobi. We'll be talking about the importance and possibilities of regional collaboration in forest monitoring. One of Phoebe's many accomplishments is as manager of the Land Cover for GHG Inventories project that developed land cover maps for 9 countries in Eastern and Southern Africa. Phoebe holds a Bachelor of Science in Geospatial Engineering and a Master's of Science in Climate Change Adaptation from the University of Nairobi. Phoebe, over to you.
Thank you, Laura. Let me share my screen. So I'll be talking about the importance and the importance of collaboration in forest monitoring. And I want to start by talking about RCMRD, which is a regional institution based in Nairobi that supports 20 member states in geospatial and IT-related services. So RCMRD strives to be a center of excellence as far as providing these services concerned in the region. And the project that has supported and delivered through this, called Survey Eastern and Southern Africa, is a joint partnership by USAID and NASA. And basically what we do is to support development activities in the areas of agriculture and food security, in weather and climate, in water and related disasters, as well as land cover and ecosystems. So why is it that we need to collaborate? And I want to refer to an African proverb that says that if you want to walk fast, you walk alone, but if you want to go far, you have to work together. And that is why we strive as an institution to collaborate where we can, because in this essence, we're able to share resources, we're able to avoid duplication of efforts, and we also take cognizance of the fact that a lot of the resources that we strive to map are transboundary resources. So if one country has very good policy and very good monitoring and the other country is not doing the same, then we are bound to fail. And through this, we're also able to share experiences, we're able to complement each other's strengths and weaknesses and are able to achieve more. So in terms of the scope of activities that we're able to support, we provide capacity building in areas of land cover and change mapping, and also in measurement of features on Earth using different tools and data. So this can be either open source or commercial tools, and also we rely on data that is readily available. So this can be optical data from different sensors or remote or radar data. We're also able to support a data development using LiDAR, and which is very critical, particularly in the component of forest monitoring. We also support this through different cloud-based platforms such as Google Earth Engine. And also in terms of responding to MRV, we're able to support statistical estimations and related activity data that is required. Further to this, we also support a reference data collection, which is critical, particularly in getting estimates of activity data, but also in collecting data that is critical in terms of supporting a training data to create land cover data, as well as monitoring. At the same time, it also provides data for validation. So we've used different tools. We've used Collectat Online. We've also used a time sync, which basically utilizes a Landsat time series. We also able to do customized data and tool development. So here we do a lot of development of body tools that support mobile data collection, either for citizen science or for forest officers who are able to submit that to a central database, and this is able to support their monitoring activities. We also support decision support systems, which is basically integrating different data that is available to be able to have a better decisions being made around land management and how that is being utilized. We support web publishing, basically making data accessible to all and sundry. And further to this, in terms of the regional and global perspective, we support forest monitoring through programs like GFOI that has tools for deforestation and degradation mapping. We also collaborate with CEOs in terms of providing capacity building. And through Digital Earth Africa, we have analysis ready data that is also supporting enhancement of forest monitoring activities. So in terms of support that we have provided in the recent past, we were able to work with FAO in the FRA assessment, that is Forest Resource Assessment in 2010, where we utilized Collectat Online to support land cover change activities in the Eastern and Southern Africa region. We also supported a program that was working in 9 countries in terms of providing activity data for greenhouse gas emissions reporting. We've also been able to support data that was used in wealth accounting and ecosystem valuation in Rwanda. And we also supported the government of Kenya in terms of developing data that was used for emission-based estimation on land-related activity. We support capacity building based on need and also based on priorities of the countries. Through a collaboration with Silver Carbon, Savir, and also this is not just the Saviris in Southern Africa, but also different Savir hubs were able to collaborate to develop a SAR handbook. So we realized that the sub-Saharan Africa has the challenge of cloud data and did not have as comprehensive application-based resources in terms of using this to better monitor forest-related activity. So through this partnership, we were able to develop a handbook that looks at different aspects of land cover monitoring on forest resources. So whether this is deforestation and degradation, or looking at forest height, or mapping mangroves, which are really critical biodiversity in Africa, and also looking at biomass estimation. So it's a very comprehensive handbook that looks at all these different components. It has manuals, it has data that you can be able to rely on as well. I want to also talk about a recent partnership we did between 2017 and 2018 that was looking at annual land cover monitoring in the Eastern African region, which was covering about 7 countries. And this was a partnership with Google, with Silver Carbon, with US Forest Department. And basically, in this particular collaboration, we were looking at how we can be able to leverage the data that is available. So the entire Landsat series and cloud computing to support annual monitoring. So this particular project had 3 key objectives. One was to support activity data provision for carbon accounting, and also support IPCC reporting. And further to this, look at different domestic related utilities such as food security, water, which is basically critical to how land is being used and managed. So for this particular project, we had 2 main activities. One is to support a statistical estimation. So basically, this was reference data collected using TimeSync tool, provide statistical estimates on the land cover changes that were taking place. And next was to provide annual land cover maps, which basically gives the spatial data that people are able to relate on how each and every location is changing and how the different forest types are changing. So basically, through TimeSync, we were able to collect quite a great resource of data. So in the 7 countries, we had about 2,000 points for each country. And in these 2,000 points, you're looking at a time stack. So from 2000 to 2017, which is basically an asset of about 500,000 data points that we were able to collect for this particular region. And actually, what TimeSync does, just back to what TimeSync does is it tracks basically the land cover of a period of time and only records when a change happens. So when a particular break point happens is when now you realize that that is actually a change process that was taking place, and you need to rely on either high resolution imagery to confirm if that particular change actually took place. So from this particular assessment, we realized that the land cover dynamics, particularly for the 7 countries we were working on, it's been such that for most of these countries, it's such that the forest cover is depreciating and the agricultural lands are actually increasing. So this graph gives a typical situation, and this is particularly for Rwanda. But you also notice that there are certain events also that led to that very rapid increase either in one particular land cover or not. So in the case for Rwanda, we noticed that around the 1998 or thereabouts, there was a very significant increase of agricultural activities, and this could possibly mean this was a period where the people who'd escaped from genocide were coming back to the country to start development and build their lives. So in using the entire Landsat time series, we were using an algorithm called continuous change detection and classification algorithm. So what this particular algorithm does, it builds a harmonic function over the time series of data for each and every pixel. So you're able to know if the harmonic function for a particular pixel stays the same over time, then it means it's probably the same land cover, no changes taking place. But when there's a break, then it shows that there's a transition from one land cover to another. So this is also just to demonstrate how Ccdc works. Basically, through the harmonic function, you can see that the amplitude changes when there's a change in land cover, and this is visibly shown just by tracking this 1 pixel over time. One of the values we realized, particularly in working with time series data, is previously we had developed data but relying on one-time data. And we realized that when you work in such a situation, it's very easy for your output to be affected by things like seasonality. By working with the time series data, you're able to track features, and even when there's a seasonality difference, you're able to see that that particular land cover did not exactly change, but it's able to pick the same feature throughout the time series. So this we found to be a very powerful tool in terms of land cover mapping. So again, in this we're able to basically understand how these different features are changing over time, and it really elaborates the value of the time series. So in one season, you see it's the same river, but it's dry. In another season, when it's wet, the river picks very well. But when you work with time series, then you're able to track the same feature over the same pixel for quite some time. So in terms of the mapping process, so we relied on the entire Landsat archive, and all these processes were being done in the Google Earth engine. So we're using the Ccdc classification algorithm and also relying on machine learning methods through random forest, and using data samples that were available in terms of either existing or data that had already been collected through other means to be able to create the land cover blocks, which were later validated to create now the final outputs. So we were also able to create a visualization platform for all the countries. So this is now through the Google Earth engine. So you can be able to select the year that you want to visualize, and this now enables you to, flip through and see where the changes are taking place. But on our classification, we relied particularly on the IPCC classification algorithm just to have regional harmonization throughout. We've also been able to disseminate the same data through ArcGIS server. So through that, you're able to visualize, compare different years, you're able to download data, and you're also able to download the metadata as well. So you can see from this visualization platform, the regional data for basically what was created. And you can also be able to use the link that is provided to be able to access the data.
Phoebe, apologies for interrupting. This is Laura, just letting you know, if you could please wrap it up. 1 more minute,
yes,
please.
This is my last one. So moving on, we are currently conducting a needs assessment in 2 countries. So basically, we understand that the changes keep the priorities for these countries keep changing. So we want to hear what the challenges are from the country. And currently, what we're hearing, for instance, in Zambia, is deforestation, degradation is an issue. Artisan mining is an issue. There is loss of forest land to agriculture, and also challenges related to timber and charcoal utilities. And further to this is the need to have capacity building as a continuous process. Thank you.
Thank you, Phoebe. Very impressive to hear all about the data you're making use of and the collaboration, many collaborations you're facilitating. Before we move on to our next speaker, I would like to welcome the many people who have joined since we started the session. And just to remind all participants that as we're going along, you're welcome to post questions in the Whova, in Slido, but you can access Slido through the link in the Whova chat if you're not already in Slido. And if you're having any problems accessing Slido, just make note of that in the chat and we will help you. Now, next we'll turn to Sam Bowers, who you saw in the intro video. Sam will provide a general introduction to the SMFM tools. Sam is a postdoctoral researcher at the University of Edinburgh, where he focuses on the application of remote sensing technologies for sustainable management of tropical dry forests and savannas. Over to you, Sam.
Good morning, everyone. Thank you very much for having me along to this event. I'm really pleased to be able to disseminate some of the results from the SMFM project. So as you heard, my name is Sam Bowers. I'm here up at the University of Edinburgh, where we worked on the technical development for the SMFM project. And what I'm going to show you is some of the technical details of what we did and describe what the SMFM tools do. But before I do that, I'd just like to quickly take a step back and talk about what is a dry forest and why is it that we're interested in them. And the question of what is a dry forest is actually quite a difficult one to answer because it depends on, the answer you get depends on who you ask. So what we're talking about here has been variously described as the dry tropics, dry forest, woodlands, savannas, or drylands. But they all do have some common characteristics which are important from a remote sensing standpoint. The first of these is that rainfall is seasonal. We have an extended dry season and the majority of the rain will fall at 1 or 2 points in the year. The result of this is a bistable system generally, where you can have open canopy cover or closed canopy cover. And these 2 vegetation structures or forms tend to be able to coexist. And the final thing which they tend to have in common is they all have a strong propensity to burn, particularly if you look at those 2 images. The situation on the left, which is an open canopy Miombo woodland, has a continuous understory of dry grasses, and in the dry season they can and they will burn. So why are they important? Well, first is they're extremely globally extensive. I've attempted in the map below to show you what that might look like. The green areas are those areas that have roughly the structural characteristics of a dry forest. And if you compare these to, say, the wet tropics, which are shown in grey, particularly in the continent of Africa, it is the drylands or the dry forests that dominate land cover. As a result, these have a very large role in the global carbon cycle. The fluxes of carbon to or from the land surface tend to have a similar magnitude to those of the more widely considered wet tropics. And as we've heard, the rates of conversion we see are rapid, and there is high demand for the goods and services. And importantly, from our perspective, is that existing forest monitoring tools tend to perform worse when applied to these areas. So existing tools tend to be designed with the wet tropics in mind, and when applied to the dry tropics, you tend to encounter problems. So, well, why do we use satellite data at all? It's not the natural thing if you want to monitor your natural resources to first lift yourself into low Earth orbit. To put the problem quite simply, it's not possible to measure enough plots on the ground. We don't have enough people, we don't have enough resources, and even if we did, it's not usually possible to access all areas. The true advantage of remote sensing of satellite data is that the provision of data is consistent and it's frequent, and it can provide data at scale. And we have no other technology that's able to do that. However, as I discussed, there are real issues when it comes to applying satellite data to the dry tropics, and I'm going to try and summarize all of those issues into the three main ones. First is phenology, that is the annual green up and leaf fall that we see. As I said, we've got a wet season where everything is looking very green, and we've got a dry season where everything dries out, and we tend to have deciduous trees that drop their leaves. The result of this from the perspective of a satellite is that some parts of the year you'll expect your forest to be very green, other parts of the year you'll expect your forest to have very little in the way of photosynthetic activity. And trying to model this annual shift and interannual shift in the greenness of your landscape provides us with a real challenge from a remote sensing satellite. This is not the same as the wet tropics, where something that is green will remain green and forests are always green. We have this annual cycle, which is difficult to model. These areas are also heterogeneous. By that I mean we have different land cover types and different forest forms that coexist within the same landscape. And let me demonstrate that by example of these two images. On the right, I've got an image of an East African coastal forest on the top and a East African Miombo woodland on the bottom. These two forms of vegetation are not occurring in different landscapes. In fact, those two images were taken about 1 kilometer apart. And the importance of this is that if you want to monitor a forest, you must expect that a forest will look quite different at different parts of your landscape and be able to account for that. And finally, as I mentioned, dry forests burn, particularly the Southern African Miombo woodlands that we've been focusing on. There is a continuous understory of dry grasses, and they provide an excellent fuel to the extent that these areas might be expected to burn every couple of years. And the importance of that is that there's a big change in surface reflectance associated with a fire, and it can be quite difficult to distinguish that sudden rapid shift in how your land surface looks and distinguish that from a deforestation event. So with this background, this is where the SMFM project comes along. So we know that we have difficulty in the dry tropics, and there is real demand for monitoring woody resources in the dry tropics. However, the existing tools and existing methods don't tend to perform so well. On the other hand, we are now in a position where our provision of satellite data is ever improving. We have better data at higher resolution, higher frequency, including both optical and radar, and these data are freely available and guaranteed into the future. So the SMFM project attempted to perform this work on the dry tropics, not simply at a national scale, but at a regional to global scale. And we did that by focusing on three countries, each with independent monitoring needs. We've got Namibia on the left, Zambia in the center, and Mozambique on the right. These three countries have quite divergent vegetation types, although they are all within the dry tropics. And the mapping needs and the monitoring needs of the organizations we are working with are all quite distinct. The importance of this is that we co-developed the method with these three teams, and the idea is that in tackling their needs, we hope that the tools will be more generally applicable to multiple locations across Africa and across the dry tropics. We had multiple methods of engaging with the teams in these countries, but I can summarize it here. We did some field work, particularly in central Mozambique and in Zambia. We worked on capacity building, and that was all based around RCMRD, from whom we just heard of from Phoebe. And we held regional meetings, and which was really the idea was to encourage knowledge exchange. There is a good deal of existing knowledge on how to monitor forests, and it's not always conveyed very well between countries. So we had a real partnership across Southern Africa here, working on these particular issues. So that's the context. For the remainder of this short talk, I'm going to explain what we did. And these are really the output of the SMFM project. We have 4 tools. For each of them, I'm going to describe how it works in brief, what it does, and what the objective is. And I'm going to show you some applied examples from Namibia, Zambia, and Mozambique of how they were used. So let's start with the first one. The building of large-scale cloud-free mosaics using Sentinel-1 and Sentinel-2 data. Now, the rationale here is that access to cloud-free images for mapping land cover can be quite challenging. It really is difficult because of the data volumes involved. However, we have these new data, particularly from Sentinel-1 and Sentinel-2, which are 2 satellites managed by the European Space Agency, which offer free data with high resolution and guarantees of data continuity into the future. And to cut a long processing story short, this is the kind of output that we get from this tool. These are 2 images. On the left, you can see an output from Sentinel-2, which is the optical satellite. And on the right, you can see an output from Sentinel-1, which is the radar sensor. The important thing about these images is they're nicely pre-processed. You won't see a cloud in them. And they have bypassed some of the difficulties of processing radar data. So while these are not necessarily a product in themselves, these are a precursor to producing, say, a national land cover map. Now, let me show you what maybe that looks like. And I'm going to use an applied example from Namibia. The region I've highlighted here is in the northeast of Namibia, it's Zambezi region, and it's probably the most densely forested and certainly the wettest region of Namibia. Now, this land cover map was produced with a particular purpose, and that was to assess a management plan for the Zambezi State Forest, from where the Namibian government were producing a new management plan, but existing data were poor, so we didn't really know where the woodlands were, where the forests were, and what kind of condition this area was in. What you're seeing on the bottom is the management plan. Particularly important features of this map are the locations of the croplands, particularly towards the east of the state forest, and the locations of the denser forests and woodlands to the west of the reserve. The other output here was identification of locations of change. Now, what you're seeing on the bottom now is a Sentinel-1 image with overlaid regions of clearance or deforestation highlighted in red. And what this identified was that really the land cover in this area was quite stable, with some notable exceptions towards the east of the state forest, which would require some special management attention. So that's our first SMFM tool, and that's for pre-processing Sentinel-1 and Sentinel-2 data, particularly for land cover and land cover change mapping. So let's move on to the second tool, and this is perhaps something which is a bit more unusual and a bit more unique to the dry tropics. What we used here was some data which from L-band radar. That is a long wavelength radar instrument, and these data were provided by JAXA. These data are now freely available, and this is quite a new situation. And the importance of that is that these data have been used for a long time at much smaller scales to monitor biomass and biomass change. And they work particularly well in areas of moderate above ground biomass. That is areas which don't have a closed forest canopy, as you might expect in a tropical rainforest, for example. And the area in which they work by far the best is this intermediate forest biomass, which you might find across much of the dry tropics, particularly southern Africa. Now, I'm going to skip some of the details here about how this works and go straight to the results. And the results we see is something like this. This is an example from Zambia showing forests in green and deforestation events in red. These kind of data are useful at very large scales for all kinds of reasons. Really, it's about monitoring of national resources, but also reporting to UNFCCC and other organizations. What perhaps is particularly unique about these data is the ability to detect some forms of degradation, and those are shown in orange. And that really is quite a unique feature, because what we're measuring here isn't forest versus non-forest. What we're measuring is a continuum of forest biomass. By identifying the changes, we might be able to detect some locations of degradation. I would like to show you maybe one other example, because I think this is particularly pertinent for the measurement of degradation, and that is the application of measuring charcoal production in Maputo. Now, as I'm sure many of those listening know, that charcoal is really one of the dominant energy resources across Africa, and really it's around 90% of urban households are cooking with charcoal, and this accounts for up to 4% of GDP. So we have this huge demand for wood fuel. However, this can put pressure on certain areas of the forest or on woodlands. In southern Africa, it's particularly the Mopani woodlands that see this. So let me show an example for the location that supplies energy to Maputo in southern Mozambique. This is what large-scale charcoal production looks like. You'll see in certain areas that you've got a lighter texture. Those are very, very large and very intense locations of charcoal production. If I zoom in on one of them, you get a pattern that looks a bit like this. The little black stripes you're seeing are large charcoal kilns in which the charcoal is produced. Up close from the SMFM fieldwork, a charcoal kiln under construction looks like this. Woody biomass is stacked into a long line. It's covered and burnt without oxygen, packed up into bags for shipping. And in the case of Mozambique, it goes out on the train to Maputo once a week from various production areas.
Sam, this is Laura.
Yes.
Apologies to interrupt. There is actually simultaneous translation into French in this session, and we heard from the translators that they would appreciate if presenters could speak a little more slowly for their benefit.
Got it. My apologies. So this is the situation that I showed you earlier from southern Mozambique, where we have a production of charcoal, and this is the view with the SMFM Alos Pulsar tool. We have areas of darker green which are showing higher biomass, and areas of lighter green which are showing lower biomass, and this is the case from Alos Pulsar in 2007. Let's go forward to 2016, and the situation looks a bit like this. And if I flick between these two images, it's fairly clear where the changes from charcoal production have occurred. If I show you a change image, I've got losses here in red and gains in blue. We can pretty clearly see those locations that have had charcoal extracted. Now, these data are really useful for classification of change. And here is what it looks like close up. We've got red areas which we're defining as deforestation or intense changes, and orange areas which are defined as degradation or less intense changes. And if I show you the original image, these areas pretty nicely line up with those areas that we can see have had charcoal harvesting. Now, this image is important because this is really the first time that this has been able to be quantified, at least straightforwardly. And I will demonstrate that by showing you what the global deforestation products might see of this area. And that's this. These are the red areas of where we're detecting deforestation. So what we can say is that at least in some locations, those areas of change that were previously invisible can now become visible through the use of radar imagery. So that was the second SMFM tool that measures deforestation and degradation using L-band or long wavelength radar. Let me move on to the third SMFM tool. The third SMFM tool uses dense time series of images to measure changes over the Sentinel-2 period and including early warnings of change. So the idea here is that we have this free imagery rolling in every 5 days. We can make use of that first to measure deforestation in the past, but also to get near real-time or rapid assessments of land cover change for management purposes. The outputs of this tool look a little bit like this. So we have areas of green, which are showing stable forest, and in the smaller blue areas, I'm indicating those locations of change that are detected. The darker blues are showing more recent changes, and the lighter blues are showing historical changes. Now, this is the example I'm showing you here is from a location in central Mozambique of around 100 by 200 kilometers. And the reason I show this is to demonstrate really this sort of scale of data processing that is required here. Just for this small area, we're talking around 1 terabyte of data. And this is not suitable for desktop processing. Whether you have a rapid internet connection or not, that's not a manageable volume of data. So it's for this reason that we apply this method on cloud platforms, cloud processing, which allows us to manage this volume of data and produce results reliably without swamping our internet connections. So let's take a look what this looks like a bit closer up. On the top, I've got some structurally simple areas where we've got changes from small-scale agriculture. As I said, the more recent changes are shown in darker blues and the more historical changes are shown in lighter blues. So we can see a progression of change in these areas and even identify the time of year that a new field was opened. On the bottom, I've got some locations which have similar forms of change, but in this case, enclosed canopy forests. And it's in these areas, the closed canopy dry forests, in which this tool probably performs the best. However, there are also difficulties on occasion, and I think it's fair to make these clear. So there are weaknesses to this kind of processing. One is in areas with high topographic complexity, the dense time series methods can struggle, and that's because you get different view angles and different shadows at different times of year. And we also detect a lot of changes in agricultural mosaics, and those we've not yet verified as part of the SMFM project. So I've got a little question mark there, but we can say that some of those changes look reasonable, and that this is perhaps a useful way of looking at the landscape. So that's our third tool, dense time series with Sentinel-1 and Sentinel-2 for deforestation mapping. The final tool I'm looking at here is classifying forest changes by type. The rationale for this tool is, as well as knowing the location of land cover changes, landscape managers are interested in the types of land cover change that are going on. And we might be able to identify those based on the size, the shape, or the intensity of disturbance events, which may be related to what's going on the ground. So here's some images from one of the SMFM field campaigns. We've got some charcoal production, we've got opening of new fields, and we have more distributed changes such as perhaps an intense fire. So this is not it doesn't tend to be a simple landscape here. We've got multiple interacting changes going on, and identifying which are the drivers of the main losses is of particular management relevance. So this is what the output of this tool looks like. It takes information based on the size and the shape and the intensity of these events and clusters them into different forms of changes. And the different changes on this map are shown in different colors, or the different classes of change. However, we do need to apply some labels to these. The tool is not able to by itself identify what's going on in the ground. So we require some degree of field work to get some ground truth, and that might identify that we've got some large-scale agriculture going on. Perhaps it's small-scale agriculture, perhaps it's charcoal production, or on occasion it can be a total mystery, either from high-resolution imagery or even from the ground. We use these data to label the different clusters. So in this case, the red cluster tends to be charcoal production, the green cluster tends to show large scale or commercial agriculture, and the orange cluster tends to show plantation forestry. And what this uniquely allows us to do is apply some kind of numbers to what activities or what drivers are causing our changes on the ground. Now, I won't keep you any longer, but one more thing to mention is that all of the tools that we produced as part of the SMFM project are open source and are freely available. So the tools are open source, they're generic, they're available on multiple interfaces, including Python, the Linux command line, FTEP through a graphical user interface, and most recently via the spatial cloud processing platform managed by the FAO. So it's there, and I'll leave it. Do feel free to put any questions in the comments. I'll try and get around to them all. Thank you very much.
Thank you, Sam. And with that, I think you also answered a couple of the questions that have come up already in the Q&A section on the most modern tools, and then also whether or not they're available open source. That was also a very useful explanation of the tools and examples of their application and how to manage the complexities in interpreting the data. We'll now turn to our final speaker in this session, Aristides Muhate, who is the MRV, Measurement, Reporting, and Verification Coordinator for the Ministry of Agriculture and Rural Development of Mozambique. Among his many accomplishments, Aristides established the first MRV unit at the ministry, and he's led national forest inventories, the development of land cover maps, and forest reference emission levels for Mozambique, and he's also been a pioneer in REDD+ projects. Mozambique, Aristides, over to you.
Thank you very much. I hope you can see me and my presentation. I will just share with you. Okay, now can you see the presentation? Okay, so I will start to present the forest monitoring and SMFM tools, the case study of Mozambique. Just to put in the context, Mozambique has about 34 million hectares of forest, about which 65% is dominated by Miombo dry forest. The recent data of deforestation indicates that Mozambique loses about 0.79% of forested areas each year, corresponding to 279,000 hectares per year. This is the historical perspective of deforestation done by province, produced in 1980s, from 1972 to 1990, produced in the early 1990s, done by Saket, which shows the area of deforestation of 152,000 hectares, and the second data of deforestation is for 1990s to 2002, done in 2005, which shows the deforestation increase in area from 290,000 hectares. So this final data was produced in 2018, and it was the time where I was personally involved in the National Forest Inventory, and when we were creating the MRV unit for Mozambique. So this is the data for each province, which shows clearly the information of logging, of deforestation by provinces. And the trends for the first time in 1980, from 2018, we could be able to understand the behavior of deforestation. By the use of open forest tools, we were able to produce the information of deforestation from 2001 through 2016. And then from 2017-18 tools, we have adopted new tools, and thanks for the SMFM Sentinel-1 project, which had a lot of inputs in improvement in our methodology to estimate deforestation or annual deforestation. So these are the driver of deforestation. Oh, sorry, these are the distribution of deforestation, the conversion of forest area to other types of for other land use types. So we have the conversion from forest to agriculture, which account to 86%, and this is basically the areas were converted to open farm to do farming or agriculture, and we have here 40% to grassland, which means that the area was converted for charcoal or logging activities. This is our guess. So there we have other conversion from forest to other land use, for example, human settlements and other land use. But then the country would need to have annual data to do the reporting. For example, now Mozambique has a emission reduction project where we have to report every year the emission reduction from that area, and we have to also to report to NTCs, UNFCCC, and there are different communication that needs to have information from the status of our forests and emissions. So the big challenge was to create a kind of a unit, a technical unit. This is what we did. Now currently we have a unit with a MRV unit with 12 technicians, and now we are producing information in a regular basis to generate estimations of deforestation currently. So, but before that, we needed that support, and the SMFM tools, these 4 tools that were very well described by other colleagues, had a very important role in the improvement and in the process of producing information for communication and decision making. So when we started with the SMFM project, we did a planning. The planning stage we did here in Maputo, which involved all the institutions, national institutions with the interest in the national forest monitoring system, and the SMFM team composed by LTS and University of Edinburgh and World Bank as well. It was the big player in this process. So after the planning, the development of the tools was done by the LTS team and University of Edinburgh, which also was very well played an important role in involving the Mozambican team during the development stage, communicating how the progress was. We had the opportunity to test and have some training in Edinburgh and in Nairobi and Mozambique with the colleagues from Zambia, and also we had opportunities to communicate with the colleagues from Namibia. So that all this process brought us into adopt learn the tools, the 4 tools, and learn and see where are the opportunities for improvements and even to in the future. And this is the result. We did some kind internal assessment, MRV unit. After the mission, we have time to do some reflection on the tools developed, all the 4 tools, were developed, and we tested all the tools developed. And seems that the tool 1, 2, and 3 are ready to use, and they are available for all available. With exception with this tool number 4, and then I will explain why it's not ready here. And the knowledge to use the tools, or the MRV unit has knowledge on these 4 tools, even in the use. The thing is that this project is about the development and testing tools. I think we should think on the implementation. During the implementation, there are some aspects that are needed to be adjusted, and in some cases, we need to do some improvements. For example, I will give you that tool number 4. The limitation is that we did the test from in certain area. We didn't cover the whole country, which that means that in some point we will need to do more sampling and to collect more training data in order to produce the outputs we want. The driver of the map deforestation type, map deforestation type, or in degradation type is very essential. We did only test in few parts in Maputo, parts of Gaza, in the central, but not. We don't think that it is very representative to use that. So as a proposal, we proposed action is that we need to increase the number of sampling data. But well, and we are working in this way, doing. We are now created a tool to collect data through PMRV, which is a participatory monitoring. We developed it through Survey 123, a form, electronic form that can be downloaded, and each participant or stakeholder with interest in forest monitoring or for different purposes can use that and collect the data. I will show you in the next slides what is that. Tool number 3, I think Sam did a good description of that, and I think that to have a deforestation and degradation map is also the question of process good. The question of having a good processing and storage capacity is something that we also discussed a lot. And we have this problem of internet, which is sometimes with the bandwidth that doesn't allow us to do much, and we are more dependent on that. So I think there we need to find ways to improve, to overcome this technology limitations. Tool number 2, we use that, and we tested with Alice Pulsar, Mosaic, and I think it provides a very good information on degradation and even deforestation. So I think the challenge now is to adapt this tool for the future challenges. We have new sensors coming, new missions coming, and it should be able to adapt. We should be able to adapt this tool to cope with the other sensors and other processes that are coming. So in tool number 1, we are not using. We currently using the Google Earth engine, and I think that our recommendation was to do the upgrade of tool number 1 just to meet the Google Earth engine capabilities, so that we can work produce the mosaics and do some processing there and generate other estimates. Currently, we are using this tool. Tool number 2 is the one that we think that we are using to generate biomass data, biomass change, and deforestation. This tool is being very useful, although we have a limitation of using ALUS data, which come 2 years after after the event, which also slows us down in terms of reporting. But I think it is something that will change in the following years as new missions are coming, and if we do some upgrades on development of this tool, I think will be very potential for degradation in biomass monitoring and biomass change monitoring. And tool number 4, as I mentioned, we developed the tool, the participatory monitoring tool, and the idea is to get the most samples possible to reduce the uncertainties associated with the identification of the driver of deforestation. So this is the testing process, and we started last year. And this is the process of producing the information required to, and that we collect the driver of deforestation in the communities. We produce the maps here. This is the kind of type of maps, as you can see here on this top left side. The map the map we produced, we print in this format. It's shown here. And we take to communities and we discuss about where the deforestation is occurring. And we also used with this map is also in here in this tablet where you can see. And we use that to orientate in the field to locate the area of deforestation. And we tested the tool using the community associations to see whether they would the difficulty of adopting this tool to collect electronically, but it seems that it's very easy, and we test that in 13 communities. And we also we gave also this tool to one partners which are working with us to test it themselves. And the results are here. We have a dashboard. This is available. I think I sent the message with our webpage, where you can see all the where you can monitor it. As people are collecting data in the field, you can see in a real time this number changing. And at this point, we have done only 25 points for testing. And you can see the driver, the confirmation that area that the detected from the sensors and our tools confirms that the deforestation occurred. And you find here also the driver deforestation. In this case, we have 100% of points where deforestation occurred, and you can see where you find the driver. For example, where is agriculture? You know what is the distribution of crops. So this is basically the experience Mozambique is having. We have here our web page where you can have access of all that information that I sent you. This is the geospatial platform where you have the geoportal, the statistics of deforestation. We have all other monitoring and measurement, other projects. So in the geoportal, you can have also access of all that information that I mentioned you. the deforestation data from 2017 up to now. You can all have access to it and get the data. This is from PMRV, where we did the testing of all data to understand where the deforestation occurred in one district, where you can see here, we can find.
Apologies for interrupting, but we need to move on to the closing at this point. There's just a few more moments for the whole event. So if you can wrap up now, please.
Thank you. So let me just finish. So I think that to finalize this presentation is we are learning, and the SMFM project has done a lot to Mozambique team, and the good thing is that we are improving tools. We developed a lot of capacity, and I will encourage the team, those who are behind the project, who support developing countries on having such capabilities, to continue to do that. And well, that's it for my side. Thank you very much.
Thank you, Aristides. Very compelling to hear your practical experiences with the tools in Mozambique. Now, with just a few moments left in the session, we are going to close with a couple of polls to learn what you think of the tools and how likely you are to use them and the obstacles to doing so. So if you're already in Slido, please go ahead and look to the polls and go ahead and fill them out. If you are not yet in Slido, have a look in the chat and Huba and follow the link to it to get into there. Here we've got the screen up where you can scan the QR code or follow the link to get to Slido. At this point, we have about 130 participants in the event, so I'm hoping to see the participation in the poll go up significantly from the 3 at this point. So we do have a hard stop on the session, so while the poll is running, I want to thank everybody for joining and participating. We do have quite a few links now in the chat of where you can get further information. So please do follow up. All the speakers in the session are very open to helping with these tools, so please do kindly reach out to any of them. And we are now moving on to the second poll of, are you likely to use these tools in your own work after these presentations? And hoping we can get to that final one. I'm glad to see many people are likely to use the tools. This is great. Thank you again for joining. And let's go ahead. I know we're still waiting for people to come in on the poll. So let's go to the final one as time allows on the challenges. Thank you again. A recording of this session will be available. Please do also visit the smfm-project.com for further information on SMFM. And again, we are here to support you in applying the tools. Thank you very much.